Hello everyone, this is Jenna Zahid and today I'll be presenting Lab 2. So in this lab, the goal was to determine the magnitude of the magnetic dipole moment mu from the on-axis data and the test dipole prediction. And we have used the fundamental formula, this formula over here, and the main result was that the experiment gave a mu of about 1.1 times 10 to the power of negative 12 am squared, and the model matched the 45-degree field within 7% accuracy. So the system was the bar magnet, and the surrounding was the phone's magnetometer, the Earth's magnetic field, and any environment interferences. The key physical ideas were the definition of a magnetic dipole, field lines, and inverse cube falloff, which were very important ideas that were discussed. And here are the formulas that we used for the dipole magnetic field calculations. And also, one of the most important topics was, or the important ideas that were discussed, were the dipole model validity when R is more than the magnitude length, or the magnet length, and the proportionality of the magnetic field to the distance R. So the initial conditions in the code were as placed here. So we have the magnetic axis location, how it's centered, and the observation points, the 3 observation points. The materials that I have used were the mobile app, the meter stick, and a bar magnet, and of course a medium to record the data. And the orientation of the phone was it was aligned east-west to cancel the Earth's BX. This is the experimental procedure on axis. These are the steps. So I have recorded the BX at multiple R values from 20 to 220, as you can see here in the table, and have found the average and locked the data in the spreadsheet. For the distance field data, I have plotted these data points and found the slope of the line, which is about -3, and that confirms the dipole behavior of the magnet. Also, I've extracted the dipole moment mu from the slope and the intercept of the log point using the equations that I presented before. And I found mu to be 1.1 times 10 to the power of -12. And I've used that in the computational model. For the computational model on GlowScript, I have edited the dipole B function to model the dipole behavior, as you can see here. This is the dipole function on the top left, and I have tuned B scale for a clear visualization of the arrows and everything, and have used the function to check the accuracy of the 45-degree model, which is here on the right. For the 45-degree off-axis test, so dperp was about 0.141 meters. And for the model, B of the 45-degree one was about 32, and the measured one was 29.8, and the difference between these two values was about 7%. For the analysis of data, particularly the similarities and differences between the experiment and the computational model, the similarities were that the magnetic field decreases with distance in both the model and the data, and the on-axis field measurements are stronger than the off-axis ones, and that matches our predictions, and the shape and the trend of the data align in both the model and the experiment. But for the differences, the model slightly underestimates or overestimates the field at certain angles, which we found to be about 7% accuracy, and the real measurements are affected by small alignment issues or external fields. And lastly, the dipole model simplifies the magnet as a point, which is less accurate as we get closer to the magnet. Our possible sources of error in this lab are the sensor placement, the dipole strength approximation, and the surrounding materials interfering with the magnet's strength, and of course, ambient metal, phone tilt, rounding, and other possible errors that are present in every lab. For our first what if question, in this experiment, you oriented your setup as to compensate for the magnetic north. So what would happen if we didn't do that? Of course, the phone would detect both the magnetic field and the part of the Earth's magnetic field along the x-axis, and this would shift all the BX readings up or down by constant bias, and the log-log slope might still be close to -3, but the intercept would be incorrect, which means that our mu value would be also incorrect. And it wouldn't just reflect the magnet's field alone, it would be contaminated by the Earth's field, and therefore it would be less accurate. For the second what if question, imagine if you had two identical magnets and they were lined up next to each other. So our magnetic dipole moment mu would double, since mu is additive for aligned magnets, and the magnetic field at every point would double in strength because B is proportional to mu, and the measured BX values would be twice as high at the same distances, and on a log-to-log plot, the slope would still remain the same, -3. It's just that the mu would probably be doubled. And these were our conclusions. So we verified that 1 over r is the proportional constant, and n equals -3, which is the slope that we found before. And mu was extracted, the models both agree with the experiment, and we have demonstrated dipole physics. For future improvements, we could do 3D mapping, and we can do finite size effects. Thank you.